Hey out there, everybody in high purity fluid process land. I'm doing a quick, I hope quick video on annealed tube bends. For those of you that do know us, we make stuff like this. And this is one of those situations where it's plug and play. These don't have the fittings on it yet, but this could be a flare fitting, a pillar fitting, whatever fitting. And that makes a connection there, and then this weaves around a bunch of different equipment and then makes another connection way over on the other side of a semiconductor process tool. These are all PFA carrying high purity fluids, mostly DI water, but in some cases slurries and acids, bases, etc. So in our prior video, we talked about PFA being fluorine and, thank you, my assistant, fluorine and carbon bond as being one of the strongest chemical bonds in known to man. And so you can't glue this stuff because you can't break it down. So, you know, we fusion weld assemblies together. We're going to have a blog come up here very shortly on fusion welding, how that works, what it means, etc. But that's kind of our core competency. We're making fluid process assemblies and vessels for high purity fluid process. Most of that's for semiconductor. When those kind of bends, first thing I showed you, started to hit the scene, people say, hey, can you guys make this kind of stuff? And we said, yeah, we think we can. I walked into one contract manufacturer and they literally had a table 30 feet long, and they had like, gosh, 20 people at a table. They all had hot air gun, kind of like this one I've got here in my hand. And they essentially were all sitting there with this thing on real high temp. This one gets up to 1100 degrees Fahrenheit. And basically they were sitting there and they were heating the tubing like this. And so I'm going to do this different than the person sitting next to me. They may not rotate the tubing. They may be 5'4". The next person next to them might be 6'3". One person might have had tequila shooters all night. The other person got a good night's sleep. Just all of the variables that could happen when you're trying to make a tube assembly. So now, essentially, they would do that. Well, and see if I don't heat it enough, it wants to actually fold. And so they would bend it, and then they would stick it in a cold water bath, which I got sitting here next to me, and let it cool down for a little bit, and then they would have this bend. So not the best, the best one. And to keep stuff from kinking, they would do the same thing. I heat this one up here, try to do this fast for video. So I'm getting this nice and hot. And what's inside there is a piece of Viton, which is a fluoroelastomer. And it's good for continuous service up to 400 degrees Fahrenheit. So now if I heat this, now that it's hot and bended, it doesn't fold. So I can stick that in my cold water bath for a few seconds. Got a bend, right? Not bad, nice looking bend. The problem with this is PFA has what's called excellent material memory. If I did this to a piece of PVC tubing, and I bent it even over a short time, it's going to sit there and hold its shape. PVC has really poor material memory. PFA, when you take it from its powder phase, turn it into a hot liquid, and then either injection mold it into fittings or extrude it into tubing and pipe, that process makes a final product that has very strong material memory. So even though that looks good right now, if I take my heat gun again, it won't take much time here. And in a lot of cases, so what? Who cares, right? The problem is, and we had one of our big customers, one of our semiconductor tool customers, come to us and say, hey, we got a problem. We can't have bins relax like that because it could get caught up in other parts of our equipment, rotating brush boxes, etc. And they said, can you make a bend that is going to hold its shape all with chemistry up to 80 degrees centigrade, which is 176 degrees Fahrenheit, you know, pretty damn hot stuff. And we thought, based on our process, which is we preheat tubing in an oven at a precise temperature for a precise period of time, a heat soak time, and then we take it and put it into a tube form that matches the assembly part number. That ensures that if I make an assembly this week, next week, 3 months from now, it's going to be identical in the center line of this bend to this bend and all of the different configurations of shape. And we thought, yeah, we think we got a pretty good methodology for how we make bends. Let us play with it a little bit. And we were able to come up with a completely annealed bend. So now we can make bends. And we tested this up to 4 hours of continuous operating at 80 degrees C. And we had less than 3 degrees differential in the bend opening from the time that we formed it. There's only 2 of us that can do this now, and the other folks, their bends move 9 to 10 degrees. So we're on a magnitude of like 3x better than our only other qualified competitor. So yes, we can do annealed bends. Our process allows us to do it quickly and repeatably. It's important. I mean, we changed the material on this coil, for instance, because I can't pull it out once and then have it stay like that. It needs to retract. So our process allows us to make, you know, DI hand spray coils and stuff for robotics that are repeating. We actually tested a coil like this on more than 1 million cycles without any deformation in the coil stack. So anyway, that's our take on annealed tube bends. We're one of only 2 that can do it, and we do it better than anybody else. So thanks for watching.